In this video, we're going to cover arithmetic operators. Arithmetic operators. On the add, subtract, multiply, and divide operations, a field specification is allowed. We use the standard field specification of 0, 5 as usual. Other fields are treated as in load A, and we'll use the letter V to indicate the specified field of contents M. So V is the value that would have been loaded into register A if the operation code were load A. So we'll see that perhaps in an example. So our first arithmetic operator is add. And it has an opcode of 1 and whatever the field is with the normal 0, 5 if it's omitted. And we say V is equal to a spec of V is the value that would have been loaded into register A. Contents M to load into RA. So in add, V is added to RA. If the magnitude of the result is too large for register A, the overflow toggle is set on, and the remainder of the addition appearing in register A is as though a 1 had been carried into another register to the left of register A. Otherwise, the setting of the overflow toggle is unchanged. If the result is 0, the sign of register A is unchanged. And we'll do an example now. So this example computes the sum of 5 bytes of register A. So first we'll start with, suppose memory location 2000 contains minus 1, 2, 3, 4, 5. And register A contains 6, 7, 8, 9, 0. If we do store A 2000, the contents of location 2000 after, so I'll say location 2000 after, because it's the standard field specification here based on the omission of a field specification, we're taking everything from register A here and putting it into memory location 2000. So this would end up being positive 6, 7, 8, 9, and 0. Okay. All right, next, we're going to do LDA, load a 2000, and we're going to give it a 5, 5. So here, load A 5, 5 has to do with this is going to be what register A is after. So I think what we're saying is we're going to take, let me try a different color here. How about red? We're going to take 5, 5, which is this index, right? 0, 1, 2, 3, 4, 5. And we're going to load it into register A. Yeah. Yeah, I think that's right. So, in fact, it would be kind of cool to do RA before and then RA after. 1, 2, 3, 4, 5, 6. So before, it's the same as what's in 2000 at this point. And then after, I think you keep the sign and then it goes in here. So it would actually be, because you're only taking one, now we go back to our color, what's happening is this replaces this, which is the same, but it gets replaced. And then the contents are fully updated after to this. So that's what that does. All right, load 2000, load A 2055. Okay, now we're going to get into the add operators. So add, oops, let me change to the actual pen tool. Add 2000, 4, 4. Okay, so when we're doing an add, we could think about register A before, and then we can think about cell 2000, and we could think about register A after. So make it a lot easier to see what's going on. So RA before is basically what's in red above is here. Cell 2000 is this 9, 0. And what we're going to do now is take the fourth index, this, and we're going to add it to RA before. So we're going to add, whoops, we're going to add all of this, all of these two things together. Add. So 9 plus 0 is 9. So I believe this should then just be plus 0, 0, 0, 0, 9. Okay. Now we're going to do add 2003. So RA before, cell 2000, RA after. So RA before, remember V is added to RA. So RA before is basically this. And then cell 2000 hasn't changed. Nine, 0. And we're going to do the same operation here. We're going to take, except it's the third index. So 0, 1, 2, 3. I'll take that and add it to this whole thing. Add. So 8 plus 9 is 17. And this will be plus 0, 0, 0, 0, 17. Okay. Keep going. Now we're going to do add 2000 to 2. RA before, cell 2000, RA after, and so RA before is really whatever was in this step above, 17. This hasn't changed. And RA after is going to be the calculation, except of the 0, 1, 2. The second index is this. We're going to add it to this. I'm going to add it to you here. So 17 plus 7 is 24. So 24 would go here, and none of the others change. Okay. Let's move on to the last operation in this example, 1, 1. And this is RA before, cell 2000, RA after. Okay, great. So similar to the pattern that we're seeing, this is 24. Nothing changes here. And we're taking the first index and we're adding it to this whole thing. 6 plus 24 is 30. So 30 goes here. Nothing else changes. So that's it. And if you add 6 plus 7 plus 8 plus 9 plus 0, that's going to equal, solve, 30. There we go. So that is the very old school way of doing it and the very new school way of doing it here using Apple's, I think they call it Apple Intelligence. All right, so this is sometimes called sideways addition. Overflow will occur in some mixed computers when it would not occur in others because of the variable definition of byte size. We have not said that overflow will occur definitely if the value is greater than, and Knuth gives 1073741,823. Where do you think this number comes from? Let's give it some commas. Well, it's going to be 5 6-bit bytes, so that would be 2 to the power 30, and we'll let Apple solve it here for us. And if you take 1 less than that number, minus 1 equals, see if you could chain them like that. I guess you can't. Okay. What I can do though, let's see if Apple will let me do this. Minus 1 equals. See if it'll let me do it. Yeah, it doesn't like the little circle I think I drew around it, but I can erase that. And I can solve it now. Try again. Solve. Really doesn't want to solve it. Oh, that's not even the one that we want to subtract from. It's this one. 1073741,824 minus 1 equals, and this should give us please. Oh, it didn't get it right. Apple Intelligence, folks. I think we can see that this is 1 less than that. Minus 1. You can see that. Overflow occurs when the magnitude of the result is greater than the contents of 5 bytes, depending on byte size. One can still write programs that work properly and that give the same final answers regardless of the byte size. Cool. So that's the add operator.